Right, howdy guys. Here's our next set of video lectures. I just wanted to show you guys this screen again so that you can see our um, lecture times, office hour times, contact information. Make sure you guys are using this contact information and emailing from your TAMU email address if you send anything to me or to Nick or Austin. Nick and Austin's SI and IA sessions are going to be starting this week. I will get the Zoom links and the schedule up on eCampus as soon as I hear back from them. Okay, just another update. The Chem 119 labs, a reminder, do not start this week. They start the following week. So they start the week of August 31st. It'll actually be online that week. So if for any reason you are quarantining and you started quarantining this past week, you should be okay. Or, well, I guess if you start quarantining anytime before Monday, you should be okay to still start in person the following week with everybody else. Again, you don't need to purchase your lab manual or the electronic course site until then. It will not be available, so don't even bother trying. If you haven't already, make sure you log on to our course site on eCampus, read our syllabus, and check out these documents if you need help getting started with ALEKS or reef polling. Or if you're new to our class, if you joined in the last few days, make sure you check there as well. You'll need to use a new ALEKS code for my class and a new reef polling course name for our reef polling in class. The introduction assignment that's posted on eCampus is due on Friday, so the 28th, this coming Friday. And just make sure that you submit it in eCampus. So if you click on the actual name of the assignment, introduction assignment, click right on that, it'll go to the page where you can submit and attach a file. Okay. You should already be aware of this and have done this, but if not, make sure you get that homework done. That is due tonight. If you're not watching this on Sunday, if you're watching it Monday morning, hopefully you already did it. All right, so let's start with some new stuff. So these are some definitions that you guys will need. Classification of substances, classification of matter. This is chapter 1.5 and also a tiny bit of chapter 5.1. So you don't really need to worry too much about looking ahead at chapter 5.1, but that will be a little bit of your homework, and I just wanted to make sure you guys knew that. So definitions of matter, elements, compounds, pure substances, mixtures, and the two different types of mixtures. So pure substances, to denote, are uniform throughout, cannot be separated by physical means. The substances have distinct properties, and those count as elements and compounds. Elements are pure substances. Compounds are also pure substances, even though they are a combination of elements. So water, for example, is a pure substance, even though it is a compound made up of hydrogen and oxygen. The only thing in a glass of water, if it's really, really pure, which is not usually the case. But imagine that the water that we use, at least in lab, is really, really pure. And it has nothing in it but water molecules. That's what we call a pure substance. An element, such as a piece of gold, if it is extremely pure gold, then it only contains gold atoms, and that is an element and also a pure substance. Mixtures, on the other hand, are two or more pure substances combined. So a mixture is more like a glass of sugar water or salt water. You can't, or even a mixture of M&Ms and Skittles. If you're some kind of crazy person that would mix up M&Ms and Skittles. So it's a mixture of two or more different things that can be separated using physical means, and we'll get into that in a little bit. So there's two types of mixtures, homogeneous mixtures and heterogeneous mixtures, and we'll talk about those in a second. All right, so just a little bit of introduction here. You're going to see a lot of different models or what's a way of saying this? Visual representations of atoms. Like we talked about in the last video lecture, atoms and molecules are submicroscopic, so we can't see them except with a really, really, really powerful electron microscope. So to represent them, scientists use models so that we can still look at the properties and behavior of atoms and molecules, even though we can't see them with our eyes. So each ball in this computer model represents an atom. So there's lots of little tiny green balls, blue balls, red balls, purple balls in this model. And this is a model of a hemoglobin molecule. So we've got tons and tons of atoms in this molecule. Some molecules, called macromolecules, have lots and lots and lots of atoms. These tend to get big enough that you can see them with electron microscopes, and they are not the most expensive of all electron microscopes, so they're still very expensive. So computer models allow scientists to perform experiments completely on a computer instead of in the laboratory. That has a lot of benefits, especially in like the drug industry, so the pharmaceuticals industry. They can make new types of medicines without ever using any actual chemicals. So they don't have to waste any very valuable reagents. They can make them on the computer and test their properties before they ever set foot in the lab. It's super cool. But I just wanted to introduce you guys to the idea of models. All right, so here are some more models. These are models of pure substances, which are elements. So I know that you can see that some of these are molecules and not just atoms by themselves. This top right one, those are just individual atoms making up an element. But some elements are actually made up of molecules of the same type of atom. So over here on the top left, this is what we call a diatomic molecule, or you'll also hear it as a homonuclear molecule in the future. That'll be later in chapter 5, I believe. But just for now, you can see that these are two atoms of the same type. They're two blue atoms combined in a molecule, but that means it's still a pure substance because they are, there's nothing else in this picture, just these two blue atoms combined. Down here, same thing, we've got groups of 3 red atoms, and they're all the same. So this is still an element because they're all made up of the same type of atom. And over here, you can see there's a whole bunch of these red atoms stacked together. This is what a solid substance actually looks like. It comes in this crystalline shape where it takes on a cubic structure. So these are all atoms of the same type, which means we can call it an element. On the other hand, we have pure substances that are compounds. So these are some common compounds that you guys have probably heard of, at least some of them. And these are molecular models of those compounds. So our first one over here is water, H2O. The hydrogens are represented as these little white balls. The oxygen is this bigger red ball, and they are connected by bonds, which are shown here as these sticks. This is called a ball and stick model. Hydrogen peroxide is similar to water, but now we've got 2 oxygens, and our hydrogens are on the end of either one of those oxygens. Carbon dioxide, we've got 1 carbon atom in the middle and 2 oxygens on either side of it. Vinegar which is also known as acetic acid, is over here. It's got 2 carbon atoms, 2 oxygen atoms, and 4 hydrogen atoms. And ammonia, so nitrogen, is typically represented as blue. You guys don't need to know this, but just fun facts. That's ammonia, NH3. So it's got 1 nitrogen atom in the middle and 3 hydrogens coming off of it. And methane, which is one of the major components of natural gas, is CH4. So we've got 1 carbon atom in the middle and 4 hydrogen atoms coming off of it. These are compounds because they are made up of more than 1 atom. All right, so, and more than 1 type of atom, I should say, to distinguish them from elements. Elements are more than 1, could be 1 or more than 1 of the same type of atom. Compounds are more than 1 different type of atom combined. This is another representation of these compounds. So this one on the top left is water, top right is nitrogen, is ammonia. The blue is nitrogen again, just like in our previous example. The bottom left is carbon dioxide. And this one over here on the bottom right is carbon tetrafluoride. So we usually use green to do different types of fluoride, chloride. Those are called the halogen family. You don't need to know that yet. But these are all also pure substances. Even though we've got different types of atoms, all of our molecules are the same thing. So when we have all of the same type of molecule and nothing else, those are also pure substances, even though they're compounds and not elements. All right, let's talk a little bit here about states of matter. So, as you know, there are 3 major states of matter. Your book goes into a few of the other states of matter in a little note at the bottom, so you can learn about plasma and Bose-Einstein condensates a little bit there. But the 3 that we need to know are solids, liquids, and gases. And this here is a picture representing water in all 3 of those states. We've got liquid water in the ocean, solid water as this glacier, and then gaseous water in the sky. So other representations of that using molecular models, we've got solid water, which has this nice crystalline structure, like I said before. So the water molecules are arranged in a very precise fashion. Liquid water, on the other hand, we've still got a lot of water molecules close together, but they're all jumbled up. They're all disorganized. And then gas, these water molecules are spread out. And that's why, so when they're in the gaseous form, they are all spread out, moving around, and we can pass through them without even noticing. All right, so another look at this. A solid is a dense material that has a defined shape, and the atoms and molecules inside of the solid are tightly packed and ordered. So ordered is the key here. Solids have defined shapes and volumes that do not come from whatever material they are in. Liquids, on the other hand, take on the shape of their container. They are still closely packed, atoms and molecules, but they can move around more. They're more fluid. They aren't stuck in this very ordered structure. So that's why liquids have a defined volume, but they take on the shape of their container. Gases, instead, have no fixed volume or shape. They move around freely in space. You can have a closed container full of gas, but you don't know exactly where the gas is in that container. It's everywhere. It takes up the whole thing. If you open your container up, they'll take up the whole space of whatever room you're in, so on and so forth. And here's an interesting fact for you guys that I thought might make this a little more fun. Cats are both solids and liquids. And this down here is a link to a journal article, an actual published paper on the fact that cats are both solids and liquids. And you can see that here. These are all images of a cat acting as a liquid, where the cat takes up the space of the container that it's in. Here it's in a wine glass. In C, it's in the sink, takes up the whole sink. And D, it's in a little bowl. So part of it sticks out. So you see both the characteristics of solid and liquid for these cats. So science can be fun sometimes too. All right, so now we're going to talk about mixtures. So air is a homogeneous mixture, which means it's a mixture of only gases, and they are combined in a way that you cannot distinguish the components from each other. So they have a uniform composition. So if you take a sample of the air over here, or a sample of the air over here, it's going to be pretty much indistinguishable. But on the other hand, soda is a heterogeneous mixture. So a mixture, it combines a mixture of all states. So we've got solid, ice, liquid, soda, and gas, carbon dioxide bubbles. You don't need to have all three of those states for it to be considered a heterogeneous mixture, but that is an easy way to distinguish that it's a heterogeneous mixture, because you can distinguish the different components very easily based on their states. You can also have heterogeneous mixtures that are all liquids, like if you have a salad dressing, you can usually see the separation of the oil and water. That is a heterogeneous mixture where they are both liquids. You can have homogeneous mixtures that are not just gases. You can have a homogeneous mixture that is a solution made up of salt and water, like salt water, or sugar water, or tea, when you got tea mixed in with your water and you can't really tell the difference. If you take one sip of tea and the next sip of tea, they usually taste about the same unless you take a really, really long time to finish your tea. A heterogeneous mixture, you can identify the separate components. Homogeneous mixture, they're indistinguishable or uniform. All right, so these are not pure substances. These are molecular models of mixtures. So you can tell because there are different types of molecules in the picture. In this top left image, we have a ammonia molecule and a water molecule, several of each spread out. So we've got two different types of molecules. That means we have a mixture of two substances. Same thing down here, we've got water, and this is actually a molecular model of acetic acid. So we've got water and vinegar. This is a dilute solution of vinegar. Both of these on the left are homogeneous because they are uniformly mixed. We've got our water and ammonia molecules spread out in such a way that we can't really find the difference. We can't take them, we can take them apart, but if we take one sample and then another sample, those samples are going to be basically the same. On the right here, we have our heterogeneous mixture. So here, the top right, we have a solid in water. So these water molecules are surrounding this solid, but this solid is not dissolving. So the solid stays in its crystalline shape, even though it's got water molecules all around it. So this would be like sand in water. So you can see the individual crystals of sand in water. They don't dissolve, so they stay as a heterogeneous mixture. This bottom right image, we have carbon dioxide and water. So this is like our soda example. We can see the carbon dioxide bubbles. We can see the gas in the water. All right, so one thing about mixtures versus pure substances, you can separate mixtures into the pure substances that make them up. If you separate pure substances, you're just going to be separating them into smaller amounts of the same pure substance. So we can't really we can't really separate pure substances by physical means, but we can separate mixtures into pure substances by physical means. On the left here, we've got some iron pieces or metal pieces in mix in with our sand. If we use a magnet, we can pick up those metal pieces and the grains of sand are not affected. So we can separate using a magnet. On the right here, we've got some images from your textbook where we've got a coffee filter being used to separate coffee grounds and water. Um, so our solid and our liquid components. We've got chromatography here. So that chromatography just means that we are separating the components of usually a liquid or a gas, but we're separating the components, it looks like maybe from a marker here or paint. We're separating the different colors that make up that marker or ink or whatever it is. And down here, this is something called a distillation, where we are separating two different liquids based on their boiling points. So we raise the temperature to the boiling point of one of our liquids, and it starts to boil and goes through this um, distillation column. So it gets separated from the other liquid, which is not warm enough to evaporate yet. So it stays as a liquid, whereas the other one travels as a gas and gets recondensed into a liquid on the other side. So we have some cooling water through this column, which causes the liquid to recondense on the other side. And this is just a little graphic for you guys to try and help you distinguish between mixtures, pure substances, compounds, elements, and different types of mixtures. So I would take a picture of this or draw your own version of this. Very helpful. All right, and just one little practice question here. How would you classify a gold bar by its composition? So let's think about this. So it's a bar of gold. Assume that this bar of gold is a pure bar of gold. There's nothing else but gold in it. What do you think? So I use the word pure, and there's nothing but gold. So it's not a mixture. So we can cancel out the last two. Is it a compound or an element? So gold is one of the elements on the periodic table. So a gold bar, even though it's a whole bunch of gold atoms put together, is still an element because it's only got gold elements, gold atoms inside of its composition. So this one is an element.